In this module, we discuss the kinetics of zeroth-order reactions. We will start by analyzing the rate law of zeroth-order reaction of a reactant A to products. We denote the concentration of the reactant as C to simplify further derivations. For a zeroth-order reaction, the rate is constant and independent of the reactant's concentration, and in fact just equal to what is formally defined as the rate constant. On the other hand, according to the definition of the reaction rate, V is equal to the negative of the derivative of the reactant's concentration over time. In this equation, we imply that the stoichiometric coefficient of A in the reaction is 1. If this is not the case, one would have to adapt the equation expressing the reaction rate via the derivative of the reactant's concentration. Combining these equations, we obtain the following expression. Negative dC by dt equals K. It is a differential equation that describes how the reactant concentration C changes over time. To find out this dependence, we need to integrate this differential equation. By doing so, we obtain a so-called integrated rate law, in this case for a zeroth-order reaction. In general, integrated rate laws predict temporal evolution in the reactant and product concentrations for reactions with an a priori known or assumed order. In essence, it's nothing else than a mathematical solution of a differential equation connecting the reactants' concentrations, as included in the rate law, with the rate of their change. To solve this equation, we also need an initial condition. Here it is given by defining the initial concentration of the reactant at the reaction start, time equals 0, as C0. In chemical kinetics, we typically solve differential equations by separating variables and integrating both sides of the equation. Here is the result of variable separation. Then, on the left side of the equation, we integrate dC from the initial value C0 to the value at any time Ct. On the right side of the equation, we integrate K by dt from time 0 to the given time t. After some rearrangement, we obtain the following expression for the integrated rate law for a zeroth-order reaction. C as a function of time equals its initial value minus K times T. This is a very straightforward expression describing a linear decrease in the reactant's concentration. The integrated rate law for a zeroth-order reaction can be graphically represented by a straight line with a slope of minus k on a plot of concentration versus time. This expression applies until all the reactant has been used up, which occurs at a time equal to C0 divided by K. After this, the concentration of the reactant remains 0. In chemical kinetics, half-life, commonly denoted as T1/2 or tau, is the time required for the concentration of a reactant to decrease to half of its initial value. It is a useful parameter of a reaction that allows a straightforward and intuitive representation of how fast a chemical reaction proceeds. To find the half-life for a zeroth-order reaction, we set C to half of C0 in the previously derived integrated rate law for a zeroth-order reaction and solve for T. That gives us an expression of C0 divided by 2K. This equation shows that for a zeroth order reaction, the half-life is directly proportional to the initial concentration and inversely proportional to the rate constant. As the reaction proceeds and the concentration decreases, the time required to reach each successive half of the remaining concentration will be shorter.